All right, so let's talk about exploring exponential functions. The basic equation for exponential functions is this right here. It says y equals a times b to the x power. The a is the initial value, which is also the y-intercept of the graph, and the b is what we refer to as a growth factor, okay? And we can also pull something called a growth rate out of that, and we'll talk about it, all right? So here is an example of an exponential function. All right, what's the initial value? Well, the initial value is 3.34. Can you tell whether this is going to be an example of growth or an example of decay? Well, it's growth because this number right here, this b value, is bigger than 1. If it's bigger than 1, it's growth. If it's less than 1, it's decay. So the initial value, there's 3.34. What is the growth factor? Well, the growth factor is the 1.67. All right. What's the growth rate? Well, when you break these growth factors up into a 1 plus something, then this becomes the growth rate. Okay, it's a rate. It'd be in the if there was a problem here, they'd be talking about something growing by 67%. Okay, so that's how you get that information out of the original equation. All right. So is this an example of growth or decay? Well, it's growth. As you go to the right, it's getting bigger. All right. Definitely growth. What's the initial value? Well, remember I said the initial value is also the y-intercept. Well, it looks to me like that's about 3. So you can tell that just by looking at the picture. This becomes a little more complicated, but so what we're going to do is the first thing we're going to do here is we're going to take two ordered pairs and we're going to find the percent of change. All right? We're going to use the percent of change formula. And so I'm just going to take these two ordered pairs basically, and I'm only going to use the y values. I'm going to say 106.77 minus 136.89 divided by 136.89. And when you do that, you get negative 0.22, and now you have found the growth rate. And so as we look at the exponential formula, I can plug that in right there. The growth factor then is going to be 0.78 because 1 minus 0.22. What we're saying is this is going down by 0.22 each time. 0.20, it's 22%, a 22% decrease. Then I'm going to pick an ordered pair from my chart. I'm going to fill in for x and y. So I'm going to use this 6 and 50.67. So I put the 6 in for x. I put the 50.67 in for y. I literally do this on a calculator, and that's 0.225 times a. Then we divide by 0.225, and we get 225.2. So now I can say y equals 225.2 times 0.78 to the x power. That's the equation for that problem. All right? So now for problem number 10, it gives you, it's a story problem. It gives you some information. It tells you the world population, 6,472,000,000. It also tells you what the population growth rate, growth rate, that's what this is. We're growing at 1.3%, all right? And this is in the year 2005. And so the first thing it asks you to do is to write an equation for the population T years after 2005. So what that means is this is going to be our beginning point. We're never going to see 2005 in an actual equation. We're just in our heads saying this is where I'm starting from. All right? We are going to see this 1.3%, but we're going to see it as a decimal, and we're going to then have this where our growth factor is 1.013. And our initial value, because we're starting in the year 2005 is this 6 billion number. 6 times 10 to the ninth is 6 billion. So that would be your answer for the part A of the problem. For part B, it says to predict the population of the world in 2015. Well, that just means put 10 in for X. And predict it in 2025, well, that just means put 20 in for X. All right? Because X stands for, that's our time period, and those are the numbers we'll put in there. All right? So you put those in, you evaluate, and you get an answer for Y. All right? Hope that helps.